In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. So I have an ammeter here, a magnet, and two coils. This coil has 100 turns and this coil has 25 turns. I will first connect the 100 turn coil to the ammeter. I am now going to take the magnet, and notice as I move it towards the coil, I get a pulse of current in the positive direction, and when I pull it out, there's a pulse in the minus direction. And notice if I just hold the magnet there, there's no current flow. It's only when the magnet's moving and when there's therefore a change in magnetic flux with respect to time inside the coil. If I move the magnet slowly, I get a small current, and if I move it quickly, I get a larger current. Okay, so it's the rate of change of magnetic flux inside the coil that determines how much current is flowing. And we see that I can get about 10 microamps if I try to move the magnet very quickly. Okay, so now let me connect the 25 turn coil. So I have 1/4 the number of turns. And so again, if I move the magnet and try to move it as fast as I can, you can see from the deflection I'm only getting about 1/4 of the current flowing. Let's summarize what we have observed. Okay, so we saw that the current was proportional to the change in magnetic flux with respect to time inside the coil. We also saw that it was proportional to the number of turns of the coil. If we were able to measure the resistance of the coil and the ammeter, we would also see that the current was inversely proportional to the total resistance of the ammeter and coil. And to complete our equation, I'm going to put a minus sign right here. Let's multiply both sides of our equation by R. So I is the current flowing in our circuit, R is the total resistance of our circuit, so I times R is the total voltage around our circuit, which we will call the electromotive force, V sub EMF. So the total voltage drop around our circuit is the same as the integral of E dot dl around our circuit. And the way to apply this equation is that if you take this closed path integral and place the fingers of your right hand in the direction of the integral, then this change in flux with respect to time, in parentheses here, is in the direction of your right thumb. And this equation is referred to as Faraday's law or Faraday's law of electromagnetic induction. The integral of E dot dl around a closed path is the sum of the voltages around that closed path. So Faraday's law tells us that that sum of the voltages around a closed path is not zero if there's a changing flux with respect to time inside that closed path. So Kirchhoff's voltage law that tells us the sum of the voltages around a closed path is zero is only correct in the DC case. Here's an illustration how Michael Faraday performed his experiment. He had a coil that was attached to a battery, so the current flowing around his coil produced a magnetic field. So he was using an electromagnet. Then he had a larger diameter coil that was attached to an ammeter. So by moving his electromagnet in and out of the larger diameter coil, he was able to change the magnetic flux inside the larger coil and see the corresponding deflection of his ammeter.